Hi, my name is Mohsen Sadr, and in this video, I'm going to talk about our new paper published in Transactions on Machine Learning Research titled Data-Driven Discovery of PDEs via the Adjoint method. This work was done in collaboration with Tohme and Kamal Youcef-Toumi from MIT. The question that we try to answer is the following. Given the data, what is the underlying PDE? Imagine you're given a data set, which is a collection of a spatial discretization of the solution at different snapshots in time. What would be the underlying governing equation described by a partial differential equation that describes the data? This is a very well-known physics problem, and there are a few methods developed in the literature for it. In this paper, we propose a new approach using the adjoint method. Without any further ado, I'm going to jump into the adjoint method and show you how the adjoint relation is derived, and then show some results comparing it to other benchmarks. To start with, we need to have a guess space for our PDE. Ideally, the guess PDE should include terms of the true PDE as well. For that reason, it makes sense to construct the guess PDE to be as diverse as possible. For example, here we have a derivative in time and summation of spatial derivatives of the solution with different orders. The goal is to find the underlying PDE by finding the corresponding coefficients here denoted by alpha. The next step is to define our cost functional. Of course, we want our estimate match the observation, so our solution F should be as close as possible to the data that is denoted by F star. The first term in our cost functional is essentially the L2 norm square error between the two. We also need to enforce that F is the solution to a PDE. This is done by including a constraint in our optimization problem using the method of Lagrange multipliers. That leads to our second term, which constrains F with the Lagrange multiplier lambdas to solve L of F. In order to regularize the optimization problem, we also incorporate an L2 norm square on the parameters of PDE in our loss function with a regularization factor epsilon 0. Before we can use this cost functional to compute its gradients with respect to the PDE parameters, first we need to find the Lagrange multipliers lambdas. We can find lambdas by actually inspecting the functional extremums of this cost functional. If we look at the total variation of the cost functional C, which is written in the top equation, and consider functional extremums with respect to f within the time interval of tj to tj plus 1, and separately for the final time at tj plus 1, we find two relations. One is known as the adjoint equation written in the middle, and the other is the final condition for the lambdas written in the bottom. This is essentially the difference between what the solution of the forward PDE gives and what the data is. Once we compute the error at the final time, we can solve the adjoint relation backward in time to find the lambdas for the whole tj till tj plus 1 time interval. Then we know everything about the cost function, and we can compute its gradient with respect to PDE parameter alpha. Let's do that. If I take the derivatives of the cost function with respect to the PDE parameter alpha, we obtain a very simple and explicit expression which requires computing integrals over space and time of the approximate f and derivative of Lagrange multipliers. Note that the second derivative of the cost function with respect to PDE parameters become positive definite, leading to convex optimization problem that is controlled by the regularization parameter epsilon 0. Once we compute the gradient of the cost function with respect to the PDE parameters alpha, we can simply use a standard gradient descent approach to update parameters of alpha with some learning rate eta. To put everything together, let's look at the algorithm of this method. When we enter the algorithm, we need some predefined learning rate eta, stopping criterion tolerance gamma, and threshold sigma for dropping out small coefficients that are close to zero. We iterate over each time interval where we have data at the initial and at the end of the time interval. And in each of them, we compute the forward solution f given the guess PDE. Then we solve the backward in time equation for the Lagrange multipliers given the final condition at the end of the time interval. Then we compute the gradient of the cost function c with respect to parameters of the PDE. Then we are ready to update our PD parameters following gradient descent. Now, if we have a very large and very complicated general guess PDE, the forward and backward solvers have to resolve all the terms that may include higher order derivatives, which are most sensitive to noise and numerical errors. Clearly, this can make the algorithm slow. To cope with this issue, we note that the magnitude of the irrelevant terms remain close to zero, and because of that, after some number of iterations, we can enforce them to be zero. This would accelerate the search if the dropout terms have higher order derivatives than the remaining ones. This is called thresholding, which significantly enhances the performance of the adjoint method. Let's consider the heat equation in 2D. We generated data by solving the governing equation and the initial condition shown in the left figure, which looks like a 2D oscillating function. The solution is shown after 20, 40, and 60 time steps. Clearly, the oscillations are smoothed out due to diffusion term. Now, given this data set, we test the adjoint method against PDE find and weak Cindy for different mesh sizes. What we have seen is that both adjoint and PDE find consistently find the underlying PDE accurately. However, as the size of the dataset increases, the adjoint method becomes more efficient, giving us more accurate PDEs at lower computational cost. In our experiments, we realized that Vixindi does not perform well, and often it gives us completely off PDEs. And to best of our knowledge, the best alternative to the adjoint method would be PDE find. For further tests, we consider heat equation in 1D, and here I'm just showing how the coefficients evolve in each epoch. That is, each time we go over our data set for the adjoint method. As you can see, in 20 up to 40 epochs, we're getting close to machine accuracy in finding the coefficients of the heat equation. Here we show the comparison between the adjoint method and the PDE find at different resolutions. Clearly, the adjoint method consistently provides more accurate solution. And interestingly enough, as the size of the dataset increases, the adjoint method remains cheaper than PDE find. For example, we obtained one order of magnitude speed up compared to PDE find while also discovering more accurate PDEs in the 1000 to 1000 dataset. Of course, we have considered other test cases. This includes 1D, 2D heat equation, Berger's equation, 1D KS equation, random walk, and 2D reaction diffusion equation. We made extensive comparisons between our method and PDE find, and what we have observed is that the adjoint method consistently outperforms PDE find for large datasets. This is mainly because of the fact that the adjoint method is able to find the gradient of the cost function with respect to the PDE parameters explicitly in a convex optimization problem. If you are interested in this topic, go ahead and read our paper on open review. We also have published an implementation of the method on the GitHub repository. If you face any challenges or problems, feel free to contact me. I would be more than happy to engage with you. Thank you for watching this video and see you in the next one.